with adding moments. We can add or in fact subtract moments, providing they are moments about the same point. Now, to make that clearer, let's do it. So there's a plank, an object in yellow. Let's mark a point on the left, P. Let's put two forces on it. I'm not saying the thing is in equilibrium, I'm just saying there are two forces on this object, a 20 Newton force and a 30 Newton force at the positions shown. And the question is this: what is the total moment of these two forces about point P? How do we combine the two separate moments? Now, if you want to try this for yourself, you can pause and think about it and try it for yourself now. Well, I hope you've had a go. Pause the video if you needed to. Let's do it. First, the 20 Newton force. Hope you can see it's got a line of action as shown there. The distance from the point where we're taking moments to the line of action is marked with the black arrow, and that distance is obviously in this case half a meter. So the moment of the 20 Newton force about point P is 20 times that distance, 0.5. And the moment of the 30 Newton force about the same point will be 30 times the distance from its line of action to P, which I hope you can see is 1.5 meters, 1 plus 0.5. So the total moment about P is obtained simply by adding them together. 20 times 0.5 plus 30 times 1.5. We've used the same point to take moments about, and we can just add the values up, giving 55 Newton meters, and both give clockwise moments, and the total moment is clockwise. Here's one for you to try. It looks the same, but if you look carefully, you will see I've reversed the direction of the 30 Newton force. So, can you find the total moment of those two forces about point P? Pause the video and have a go. Let's go through that. First of all, let's do the clockwise moment separately. The 20 Newton force produces a clockwise moment, as in the first question. It will be 20 times 0.5, 10 Newton meters. Because we've reversed direction, the 30 Newton meters produces an anti-clockwise moment. 30 times the distance to the point from the line of action, it's 1.5 meters, so the anti-clockwise moment is 30 times 1.5, which is 45 Newton meters. So we've got two moments, but they're in opposite directions. Now the biggest one is 45 anti-clockwise. Some of that is basically cancelled out by the 10. So to get the total, we've got 45 anti-clockwise and 10 clockwise. The total will be 45 minus 10, which is 35 Newton meters anti-clockwise. Now, it's very important that you understand what's on the screen, so if that's not clear, pause, read it through carefully, and make sure you have got the idea. Now, here's a little exercise to test if you understood. We've got four 10 Newton forces acting as shown. That's the four arrows in the diagram, each is 10 newtons. Can you find the total moment of these forces about P? Pause and try that for yourself. Okay, let's go through it. Let's do the clockwise moment first. There's two clockwise moments to add. 10 newtons times 0.5 plus 10 newtons times 1.5. Yeah? 10 times half plus 10 times 1.5. That comes to 20 Newton meters. The anti-clockwise moments are the lower forces pointing upwards on the diagram. They will have a total anti-clockwise moment of 10 times 1 plus 10 newtons times 4 meters. That's where we get those numbers from, giving 50 Newton meters anti-clockwise. We've got to get the total, so we've got to combine the clockwise and anti-clockwise, and I hope you can see that the total will be 50 minus 20, which is 30 Newton meters anti-clockwise. The overall direction is given by the bigger of the two, which is the anti-clockwise 50. Gives you the direction of the final. Let's talk about sign conventions that we can use when talking about moments. We often use clockwise moments. We give them positive values, and anti-clockwise moments are given negative values. What does that mean? Well, let me show you the calculation we've just done. Hope you recognize that. It's just the problem we solved a moment ago. How would we do that using a sign convention for moments? Well, we'd do this. We'd say the total moment about P is, and we go round adding the moment of each force. So the order doesn't really matter. Let's do it left to right. 10 times 0.5, that's 10 newtons times half a metre is the first moment. We then add the second of the moments, which is 10 newtons times 1.5. That's the second term. Bottom left, we've got 10 newtons times 1. But it's producing an anti-clockwise moment, isn't it, that lower force? So it's 10 times 1, but because it's anti-clockwise, we use our sign convention, anti-clockwise negative, and we add minus 10 times 1. And the force on the right bottom, it's 10 newtons times 4 meters, but it's anti-clockwise, so we're going to add minus 10 newtons times 4. We do the arithmetic, and it comes to minus 30 Newton meters. The minus sign tells us the overall direction of the total is anti-clockwise. Now, when we add these terms using plus and minus to indicate the clockwise or anti-clockwise sense, we give the sum a name. We call the sum the algebraic sum, or sometimes called the vector sum, of the moments. It's this expression here. We've added the moments. Some are positive, clockwise ones. Some are negative. Those are the anti-clockwise ones. And the overall sum of these four terms is called the algebraic sum. The term vector sum isn't actually technically correct, but you'll hear it used. It's best to call this sort of sum the algebraic sum of the moments. And before we finally talk about the principle of moments, what do we mean by rotational equilibrium? Well, we're talking about static systems at the moment. And let me give you a definition. An object is in rotational equilibrium when it is not rotating, not turning, not tilting. Simple as that. If it's stationary, it's in rotational equilibrium. Now later on, when you learn about dynamics, that's moving systems, you learn that rotational equilibrium means a bit more than this. It actually means an object is rotating at a constant rate. It's not speeding up or slowing down in its rate of rotation. And of course, a constant rate of 0 corresponds to not rotating at all. So for statics, stationary systems, by rotational equilibrium, we simply mean it's not rotating. Okay, bear that in mind. Now, what is the principle of moments? Well, I'm going to give you a very simple version first of all, and then a more sophisticated version in a minute or two. Here's the simple version. If an object is balanced, the total clockwise moment about the pivot equals the total anti-clockwise moment about the pivot. I hope that is common sense. Let's do an example. There's an object, plank. Let's suppose it's balanced at its centre of gravity. The pivot is at the centre of gravity. What that means is the weight of the plank itself acts through the pivot and has no moment. So the weight of the plank doesn't alter the balance. So the only two forces we need to worry about are the one on the left, marked F, and the weight of the object on the right-hand side, 10 newtons. And if the plank is balanced like this, we can draw the lines of action of those two forces. I could give you information about the positions of those forces, and I could ask you to find how big force F is. In fact, why don't I do that? How big is force F? Can you pause the video and try working that out for yourself? Pause now. Well, I hope you had a go. Principle of moments, this thing is balanced. What's a clockwise moment? Well, it's 10 newtons times the distance from the line of action to the pivot is 1.2. Clockwise, it's 10 times 1.2 newton meters. Anti-clockwise, it will be F times 0.6. So, from the principle of moments, we can write this equation down. Clockwise moment equals anti-clockwise moment. 10 times 1.2 was the clockwise. The anti-clockwise was F times 0.6. Then all we have to do is rearrange the equation. It gives us 20 newtons for F. Hope that makes sense. That's very important. Again, if it's not clear, pause, look at that very carefully.